Scientists have made an extraordinary discovery with NASA's James Webb Space Telescope, Supernova Hope. This rare, gravitationally lensed Type 1 supernova is not just another explosion in the universe. It's providing researchers with a powerful new tool to measure the expansion rate of the cosmos, known as the Hubble constant. Even more exciting, this discovery could help solve the long-standing debate in cosmology called the Hubble tension. So, what makes Supernova Hope so important, and how does it contribute to understanding the universe's expansion? In this video, we will explore the answer. Supernova Hope is a special kind of supernova, one that was observed through a phenomenon known as gravitational lensing. Gravitational lensing occurs when a massive object, such as a galaxy cluster, bends the light from a more distant object, creating multiple images of that distant object. In this case, the galaxy cluster PLCK, located 3.6 billion light-years away, acted as a lens, splitting the light of a supernova in a galaxy far behind it into three distinct images. This effect is incredibly useful for astronomers because it allows them to observe objects that would otherwise be too faint or distant to study in detail. But what makes Supernova Hope even more interesting is that it's a Type 1a supernova, a type of exploding star that has a predictable brightness. This type of supernova is often referred to as standard candles because their intrinsic brightness is so well known that astronomers can use them to measure distances across the universe. This makes them critical tools for understanding how fast the universe is expanding. Now, you might be wondering how exactly astronomers discovered this supernova. In 2015, the Hubble Space Telescope took images of the same galaxy cluster, but the supernova wasn't there. Fast forward to when Webb's guaranteed time observations of the prime extragalactic areas for reionization and lensing science, PEARLS, program snapped images of the cluster in 2023. The team noticed three dots of light that weren't present in the Hubble images and immediately suspected that they had found a new supernova. When Webb's data arrived, the team led by Brenda Fry from the University of Arizona quickly analyzed the images. They were excited to confirm that the dots were indeed a supernova that had exploded in a galaxy much farther away than the galaxy cluster acting as the lens. The gravitational lensing of the galaxy cluster splits the supernova's light into three images, which is like seeing the same star explode at three different moments in time. And just like that, Supernova Hope was born. Type 1. A supernovae are incredibly reliable tools for measuring the expansion of the universe due to their predictable nature. This predictability comes from the explosion process itself. This type of supernova occurs when a white dwarf star, the remnant of a smaller star that has exhausted its nuclear fuel, accretes material from a companion star. Once it reaches a critical mass, a white dwarf undergoes a thermonuclear explosion, releasing a consistent amount of energy. Supernova Hope fits perfectly into this model. Astronomers can accurately determine its distance by measuring how much its light has dimmed on its journey to Earth. This brings us to the Hubble constant, a key parameter in cosmology that describes the universe's expansion rate. To measure it, astronomers need two pieces of information: the distance to faraway galaxies and the speed at which they are receding. This type of supernova provides the distance, while redshift, the stretching of light caused by the universe's expansion, reveals the velocity. This brings us to the Hubble tension, which is a discrepancy between different measurements of the Hubble constant. Local measurements, including those using T-fields and supernovae, tend to give a value of around 73 kilometers per second per megaparsec. However, observations of the early universe, such as those from the cosmic microwave background, CMB, measured by the Planck satellite, suggest a lower value of about 67 kilometers per second per megaparsec. This gap between local and early universe measurements has been one of cosmology's biggest challenges. Enter the SHOES project, led by Adam Rees, which has been at the forefront of using Type 1 supernovae to measure the Hubble constant. This project has played a significant role in highlighting the Hubble tension and has consistently found a higher value for the Hubble constant. Supernova Hope adds another layer of complexity to this debate, by providing an independent method for measuring the expansion rate through gravitational lensing. But Supernova Hope isn't the first lensed supernova to contribute to this discussion. The discovery of IPTF16 GU, another gravitationally lensed, Type 1a supernova observed by the Hubble Space Telescope, also provided a new way to measure the Hubble constant. Similarly, SN-REF-STAL, the first supernova observed to be gravitationally lensed multiple times, allowed astronomers to study time delays and refine their measurements of the universe's expansion rate. However, Supernova Hope stands out due to the precision of its measurements, enabled by the James Webb Space Telescope. Its advanced instruments allow for unprecedented accuracy in observing lensed supernovae, helping to refine our understanding of the Hubble constant. The initial measurement of the Hubble constant from Supernova Hope, 75.4 kilometers per second per megaparsec, still shows some tension with values derived from the early universe, bringing us closer to resolving this long-standing issue. Now, let's explore some theoretical models proposed to address the Hubble tension. One prominent theory that could resolve the Hubble tension involves self-interacting dark matter, SIDM. In this model, dark matter particles are capable of interacting with each other, unlike in traditional models where dark matter is thought to interact only through gravity. These self-interactions could affect how structures formed in the early universe and could influence measurements of cosmic expansion. Additionally, evolving dark energy, the mysterious force driving the accelerated expansion of the universe, could play a role. Changes in the behavior of dark energy over time help explain the discrepancy between local and early universe measurements of the Hubble constant. Another possible explanation for the Hubble tension lies in modified gravity theories. One such theory is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently on cosmological scales than predicted by general relativity. In MOND, the laws of gravity might need adjustment when applied to considerable distances, such as those between galaxies. This modification could reconcile the differences between local measurements of the Hubble constant and those based on observations of the early universe, such as the cosmic microwave background, CMB. The idea behind modified gravity theories is that our current understanding of gravity may need to be revised, mainly when applied to the vast scales of the universe. If these theories hold, they could provide an alternative explanation for the Hubble tension without needing to invoke dark energy or dark matter as the primary factors. Thanks for watching. Please like, subscribe, and hit the notification bell for more exciting cosmic discoveries. See you in the following video.